For those who've seen vectors, by all means skip these videos, go straight to the practice problems. There's no need to mess around here. This is an introduction for those who have never seen a vector before or have seen them briefly and just would like a gentle reminder about how they work. All right, a vector. Definition. A vector is a quantity that has both a magnitude and a direction. What distinguishes that from other values we've seen up till now is that if you have magnitude only, then that's something called a scalar. And length, volume, temperature would be scalar quantities. There's things that you measure and things are 30 degrees and you're done. When you talk about velocity and force, it's always a certain magnitude in a certain direction. I'm moving 5 meters per second towards the east. I'm applying a force upwards on an object. Those extra qualifiers, if they can be added, basically make your force or make your velocity a vector quantity. I can't say a temperature in the upwards direction or a length in the length. Ouch. The length itself is not in the upwards direction. It doesn't have a direction in and of itself. I certainly can't talk about volume with a direction either. So maybe the length was poorly chosen as a role model there. A length is just a fixed quantity. This thing is so long. That's all we care about. If there's multiple lengths, then those other words just tell you which length you're talking about. When we talk about vectors, we also have a graphical idea in mind almost every time we talk about them, and we typically use the arrow notation. So we're going to use that throughout this course. The idea is there's a base somewhere, and the vector is the same regardless of where it's located. So these vectors are all the same vectors, as long as they have the same direction and the same magnitude, which as a single quantity, notice length is back here again, represented by the length of the arrow, then we'd say that all three of these represent the same vector quantity. All right, we've got a scalar axis here. I'm going to draw some vectors on here. 0, 0 to 1, 2, 3, 4. There we go. 2, 2 to 5, negative 2. 2, 2 to 5, negative 2. There we go. And, sorry, I should add some arrowheads on these. This is the source, and that's the 2. So notice the 2 from makes a difference. Negative 1, 3 to 2, 7. 2, 7, so there to there. And the arrow from 1, 2 to negative 2, negative 2. All right. So if we look at those vectors, this vector and this vector, we would say are the same, because they have the same difference from their source to their 2 location. This one here is similar, but opposite direction. And the directionality definitely matters. And we'll see how to represent opposite directions as we continue our study of vectors. And this one here is just different. Same length, but different direction. So not the same vector at all. What can we do with vectors? Well, we're going to do a whole bunch of things with them. Let's start off with the basic operations, beginning with addition and subtraction. So someone hands you a vector moving due east this much, another vector heading northeast with this magnitude. If we add these two vectors, we talk about head to tail. So v1 plus v2, and we use these little arrow hats to indicate these are vector quantities. When we talk about the graph of this, we're going to put the vectors head to tail. So in other words, we move v1 out, and then we put the tail of v2 at the head of v1, so we get a net vector like so. And that quantity there would be v1 plus v2. There we go. I can take the differences, and there's two ways to think about the differences. I like to think of it as the first vector, v1, we sketch out where v2 would have gone. That didn't work so well. Let's try that again. And in our case, we draw it in the opposite direction. So this is negative v2. What I mentioned in the last slide about things being the opposite direction, having a certain relation to the original, we can express something moving in with the same magnitude but the opposite direction as a negative. And other people have learned different head-tail constructions here. I like doing it just as the negative because it's something that plays a role later on, and we see it that way. The resulting vector is this connection here, and so that would be the vector v1 minus v2. Last but not least, we could talk about doing v2 first. So v2 goes up at that angle, and then instead of taking v1, we would go in the opposite direction of v1, and here's our v2, and so the resulting vector there would be v2. We kept it as is, and then we subtracted or went in the opposite direction of v1. And in fact, not surprisingly, you see that these two vectors look similar, except wait, they're opposite directions, but same magnitudes. Why? Well, if I put a negative in front of all this, I would get this expression here. So a lot of the algebraic manipulations that we do with regular numbers and variables apply to vectors. We're going to see where that breaks down when it comes to multiplication, but certainly for addition and subtraction, vectors behave like you would expect. What about a couple of special quantities here? If I have v1, let's go straight east. Goodness, I did something odd. Straight east. And then we said, well, that would be another v1 if I added another v1, but I'm going to actually go back the opposite way in exactly equal amounts with the negative part of v1, or the negative contribution of v1. And so the net is just a point. And v2 minus v2, it's exactly the same thing. We would go up 45 degrees and then back down. And the net change there would just be a point. This point has a special meaning, or special name. It's called the zero vector, and it has zero length. And it is the only vector which has no direction whatsoever. I can't talk about this point being in the northeast direction or anything else. This vector I can because it has a non-zero length. Oh, once I have some length, then it has to go in a direction. But if it has no length, I can't define a direction. So that's an important property of the zero vector, which is going to be, again, helpful on the calculation side that we see later when we come to derivatives. For now, it's simply enough to note if I add a vector and subtract it off again, I get the zero vector, sometimes written as 0 with a hat, and that is the only vector we can talk about which does not have a direction.